Hello everyone and welcome. In this video, let's learn how to evaluate type 1 improper integrals. Now, what's a type 1 improper integral? Well, a weird looking integral where you can see infinity or negative infinity or both negative infinity and infinity in the limits of the integral. If you can see that, then that's a type 1 improper integral. Just like here, you can see infinity in the upper limit of the integral. Now, what's the big deal with improper integrals? What's the problem with having infinity? Let's try to understand this geometrically and mathematically. What's the problem with infinity? Well, geometrically, we already discussed this. What this integral means is that if this function is this curve, if this curve is e to the negative 2x, you have to calculate the area under this curve from negative 2 to infinity over the infinitely long interval negative 2 to infinity. At least it doesn't sound practical, or it sounds weird, right? So you want to find this area that seems to be like it's going on forever. At least the interval that you are finding the area over is going forever, right? Okay, so that's geometrically something weird. Now let's see mathematically. Because e to the negative 2x, it's not the hardest function to integrate. Now if you integrate e to the negative 2x, you get e to the negative 2x over negative 2. Now since this is a definite integral, you just need to evaluate the function at infinity and negative 2 and subtract. Now evaluating the function at infinity, mathematically that's problematic. That doesn't make sense because infinity is not a point where you can go to that point and stand on it, right? You cannot evaluate a function if you cannot evaluate a function at infinity. So mathematically it doesn't make sense. That's the deal with infinity. That's the problem having infinity in the limits of the integration. Okay, now how can we fix this? Think about this integral. Well, if you have to integrate this function from negative 2 to 5, well, it makes sense in every way, right? What is this asking for? So to find the area under the curve from negative infinity to 5. So it's just basically asking you to find the area in this enclosed finite region, which makes sense. And if you had to integrate this, you can do this, right? Because the interval is finite. Okay, so the bottom line is if you can have a finite interval, then everything is fine in type 1 improper integral. Okay, so how can we make this integral a finite one, at least to integrate over a finite interval? Okay, because integration here is the problem. Here's what we can do. Here's the fix. Okay, so you want me to integrate e to the negative 2x from negative 2 to infinity, but let's say I don't like infinity, so I'm gonna replace it by a finite number. Let's choose a finite letter t, not a number, I'm sorry. Okay, so I'm gonna replace infinity by t, a finite letter. Okay, t is a finite number. A finite letter means a finite number. Okay, t is a letter, it's a finite, think it as a finite number. So let's say t is like here, t is 1 2 3, a finite number. So now this makes sense. Now this integral makes sense because you are integrating over a finite interval from negative 2 to t. Can you evaluate the function at t? Of course, yes. Just plug t for x. It's not like plugging infinity, right? Okay, now what I'm going to do is I'm going to move at the same time t to infinity. I'm going to make it large gradually. So I can explain that by taking the limit of this integral. All right, now what happened here? I replaced the infinitely long interval negative 2 to infinity by a finite interval negative 2 to t, and then let's move that t slowly towards infinity. So that's what I did. Now this is a great fix. This is an amazing fix because what you have done here is now you have created something that where you can integrate and evaluate. Here to start with, you cannot integrate this. I mean, you can integrate, but you cannot evaluate because of the infinity. Okay, now you fix that problem. Okay, now you can evaluate what you get after integrating after integration at t and negative 2, evaluate and then take the limit. Okay, all right, so let's see what's going on. So first of all, evaluate the integral because we know how to do that. So if you evaluate e to the negative 2x, you get e to the negative 2x divided by negative 2. That's the integral of e to the negative 2x. Now you want to evaluate it at t and negative 2 and subtract. So let's evaluate this at t. If you plug t, so it's e to the negative 2t divided by negative 2 minus, now substitute negative 2. Now if you substitute negative 2 for x, this is e to the 4 divided by negative 2. Let's simplify a little bit. Now take the limit of the function e to the negative 2t over negative 2, negative plus here e to the 4 over 2. Now think about this. Here you just need to take the limit of a function. Now rather than evaluating a function at infinity, taking the limit when t goes to infinity makes sense, right? So that's the bottom line here. That's why we take the limit. So this is a very nice, neat trick in mathematics in regards of improper integrals. Okay, now what's the limit here? Now when t goes to infinity, e to the negative 2t, that goes to 0, right? That decays down. That's a decreasing function. It goes to approaches to 0. So 0 plus e to the 4 over 2, e to the 4 over 2 is a constant, so limit of a constant is that constant, so it's e to the 4 over 2. That's the limit. Guess what? This is the value of this improper integral. Now even though you are integrating over an infinite interval, you get a finite answer, right? E to the 4 over 2 is a finite number. It's not infinity, right? See, now that's what happen here when you use this nice little trick. Okay, so you replace that upper limit infinity by a letter and take the limit. Okay, right. What this means is that even though this area seems to goes forever, the area is not infinity. It's e to the 4 over 2. Okay, all right, so let's do another example where in the lower limit we have negative infinity. Now this is the second example. Now you can see this is a type 1 improper integral because in the lower limit we have negative infinity. And that's a problem. Like we discussed in the previous example, once you integrate e to the negative 2x, you will have to evaluate at negative infinity. That's a big no-no, okay? So geometrically what this means is you have to find the area under the curve e to the negative 2x from negative infinity until the x point 2. So you're finding the area in this region and it goes on forever, right? The interval is infinitely long. So what's the fix? Now you know the fix. So you want to integrate negative infinity to 2. You want to integrate e to the negative 2x from negative infinity to 2. So I'm going to replace negative infinity by a letter and make the integral, make your interval finite so that you are integrating over a finite interval. Now t2 into, that's a finite interval. So it's like t is somewhere here. So I'm integrating this region. Now let's slowly move t towards not infinity, negative infinity, because we have negative infinity here. So let's take the limit when t goes to negative infinity. Okay, right, now we can easily evaluate this integral. Okay, keep on writing the limit, don't drop that. Okay, this is something that I have seen when I grade exams. Students drop the limit when you're doing the calculations. No, you have to keep it. Okay, now this is a one statement, it's not two statements. Okay, it's a one thing, so I have to keep writing the limit. Now let's integrate e to the negative 2x. We already know that it's e to the negative 2x over negative 2. You have to evaluate it at 2 and t and subtract. Now let's evaluate it at 2. So limit t goes to infinity. If you evaluate it at 2, it's e to the negative 4 divided by negative 2 minus subtract. Now evaluate at t. Now t is a finite number. E to the negative 2t divided by negative 2. Now we can write this limit t goes to infinity, e to the negative 4 over negative 2, negative positive, e to the negative 2t over 2. Fine. Now let's take the limit. Now you just need to take the limit of a function. It makes sense rather than evaluating a function at negative infinity, right? Okay, I made a mistake. So even though I said t goes to negative infinity, here I wrote t goes to infinity, but that's wrong. T goes to negative infinity, okay? All right, that's an error on my part. Now, when t goes to negative infinity, the limit of this constant, well, it's the constant itself. But this part, when t goes to negative infinity, e to the negative 2t, now that doesn't go for 0, okay, go to 0. This gets extremely large, okay. So when, think about this function gets large and large when x goes to negative infinity, right? So it goes to infinity. So the limit of this function is actually infinity. Infinity plus constant, it's infinity. All right. So now that means if you when you integrate the function e to the negative 2x over the interval negative infinity to 2, you get infinity. That means the area is infinite. Okay, the area is infinitely large, and which makes sense kind of pictorially, right? Like it seems to be like here the area is getting bigger and bigger, you know, it's not enclosed, so it makes sense pictorially, and we verified it mathematically as well. All right, the bottom line here is that if you are integrating a type 1 improper integral, so a to infinity, what you do is you write this at, you replace the infinity by a letter, okay, right, and take the limit. Take limit t goes to infinity. Now if you have negative infinity on the lower limit, well, you do the same thing, except you take the limit when t goes to negative infinity and replace the negative infinity by a letter t. Okay, so that's what we do to evaluate type 1 improper integrals. Now what would you do if you have both negative infinity in the lower limit and infinity in the upper limit? So how do we evaluate this improper integral? Well, I will teach that in a separate video when I'm doing a lot of examples. Okay, I don't want to make my videos too long. Okay, so it's already exceeds 10 minutes. So I will teach this when I do a lot of examples from type 1 improper integrals. Okay, all right. So in the next video, let's learn the idea convergence and divergence. And then after that video, I will do a lot of examples from type 1 improper integrals. Okay, and when I'm doing a lot of example, I will do this type of an example as well. All right, so I'll catch you in the next video. Bye bye.